Hi, how's it going? My name is Carl Diaz with the Learning Resources Center here at the University of Colorado, Denver. Today we're going to be talking about concepts associated with temperature. So let's get going here. First of all, like with every video, we wanted to kind of define what we're talking about. So temperature is kind of a weird thing because, if you were probably asked to describe it, you would probably have, you've probably never been asked, but you might have some difficulty determining it because the way we measure temperature isn't exactly what temperature is, because temperature of a system can change, right? Like your body isn't always the same temperature. The temperature of a room isn't always the same, right? So temperature isn't a set thing. That's why it's hard to define it. So when we define temperature, we're defining it as a quantity that determines when objects are in thermal equilibrium. So what the heck does that mean? Well, let's use an example of like it's really cold outside. Let's say it's winter time outside and it's freezing cold outside, and you come from outside and you walk inside and it feels really warm. Well, why the heck does it feel warm for you? Let's say you're not wearing a jacket either. Let's really go to extreme here. So you're outside for some reason in the freezing cold, it's snowing with no jacket on, and then you walk inside a building with the heater on, and the temperature is really warm. Why does that happen? Well, it happens because your body is trying to come into thermal equilibrium with the system, right? The system is your environment in this case. So when you're outside, your body's trying to come into thermal equilibrium with the outside, the temperature outside, right? And so what happens is that you can't lose, cold can't be transferred, right? So I know you've probably heard your mom, your dad, they tell you, close the door when it's cold outside, and they'll tell you, you're letting all the cold air in. Next time they tell you that, you go, that's not true. What's happening is the heat's going out, right? So the only thing that can transfer is energy. And so heat is the thing that transfers. So when you go outside, you go from a hot environment to a cold environment. So you go outside, what happens is your body starts losing heat. And then when your body starts losing heat, your neurons send a message to your hypothalamus and tells you that there's a change in temperature. And you register that as cold. You're getting colder. But why does it feel like you're getting colder? Because your body's losing heat. You're trying to come into equilibrium with the outside temperature, and if the outside temperature is cold, that cold can't transfer to you. So how do you come into equilibrium with the system? You're going to have to lose heat. So you start losing heat to the environment, and then that transfer of heat, you'll stop losing heat to the environment when you start to come into equilibrium with that environment. It's the same thing when you come inside. So you're outside in the freezing cold, and then you come inside when it's night where it's nice and warm, you start to feel hot. Well, why? It's not because the cold is going away, right? It's because now you're trying to come into thermal equilibrium with the new environment that you're in. This is an environment with the heater on, and now the heat's coming to you, right? You're very cold. You were coming to equilibrium with the outside temperature, so you started to lose a lot of heat. When you come inside, now you start to gain a lot of heat. Your body, again, registers that into your brain as a change in temperature, and you recognize that as heat, but that's why you're warming up. So it's the transfer of energy, right? So things come into, as you move from certain environments, your temperature is going to change based off of you coming into equilibrium with it. If you walk into a room that's relatively the same temperature as you, that you're not going to feel much of a change in temperature. You're not going to feel cold or warm because you're already somewhat in equilibrium. Yeah, there might be a little transfer back and forth between the environment, but you are somewhat in thermal equilibrium with that environment, so you're not going to feel the change as much. Okay, so that's what's important. Temperature of all things can change. There's no set temperature for things. Temperature changes based off the transfer of heat. So heat will move from one system to the other, not cold. Cold doesn't move. Cold doesn't make any sense to move. All cold is in what we're going to talk about here is when the atoms aren't moving. Okay? So what happens is the faster and faster, and we're going to talk about this in a second, but this is the concept. The faster and faster that the particles are moving in the environment, the faster and faster the harder they're coming in contact with anything in that environment. When those atoms in that environment collide with anything in that environment, there's a release of heat in that collision. So it collides and there's a release of heat, all those atoms, right? And this room that I'm standing in right now is jam-packed with atoms. All those atoms are moving at a certain speed. All those atoms not only are moving at a certain speed, but they're colliding with me, right? They're having a change in momentum. There's a change in pressure, or I'm sorry, not pressure. Pressure is related. The pressure is related to the impulse, right? So there's a change in momentum. Change in momentum's an impulse. That's the amount of force there, right? In that collision, right? The harder the collision is, the more thermal energy is released in that collision. So the faster the particles move, the harder the collisions, the more thermal energy is released. And if thermal energy is released in that collision, your body's going to absorb that thermal energy if it's a lot, and so that'll be transferred. So that's what's going on. That's where the energy is coming from. It's coming from the atoms. That's why when we talk about temperature, we have to talk about the atoms. We're talking about the speed of the atoms, right? And how they're making collisions. That's what we're talking about. All right. That's what determines the temperature of the room. So the temperature in the room is determined by how fast the particles are moving. When you walk into that environment, or something comes into that environment, those particles start to collide with it, and based off the temperatures of those two systems, that thermal energy is either going to be transferred to or from the system until those systems come into equilibrium. The transfer of energy between those systems is balanced. There's really no more transfer. The energy is staying stable. That's what equilibrium means, okay? So keep that in mind, all right? When your parents are harping at you and stuff about leaving the door open, you can come right back at them and say, hey, cold doesn't come in and out. I'm not letting any of the cold air in. I'm letting the hot air out. So that's the big idea. Systems come into equilibrium. How? By transfer of energy. You go outside where it's cold, you start to lose heat. You come inside where it's warm, you start to gain heat, okay? And that's how thermal equilibrium is established. That's how you establish equilibriums between systems, okay? So temperature is, this idea of temperature is based off of the laws of thermodynamics. Thermodynamics is essentially dictating these ideas when it comes to temperature. So the first law of thermodynamics, it's not the first law of thermodynamics, it's called the Zeroth Law of Thermodynamics, because we found it later. We actually realized it should come at the beginning. It tells us if two objects are in thermal equilibrium with the third object, that the two objects themselves are in thermal equilibrium. So the way to digest that is to think like this, but it's trying to tell us a little bit more. So let's say this red object's in thermal, it's in thermal equilibrium with this green because they're touching, right? It's also in thermal equilibrium with this blue box because they're touching. But since they're both touching the red box, the green and the blue boxes will also be in thermal equilibrium with themselves. So that's just something that we know and understand. It's the way thermostats kind of take on this idea and work on that idea. But the idea the bigger idea to take away from the Zeroth Law is it helps us kind of define temperature, right? Because I could have two different temperature scales. I can have a temperature scale that reads in Kelvin, and I can have a temperature scale that reads in Celsius, right? Well, I can take both those temperature scales, right, and put them into this room, right? Well, they're measuring difference here. One's going to tell me a different number than the other one, right? But they're both coming in thermal equilibrium with the room, and if they're both in thermal equilibrium with the room, that means that both those temperature scales are in thermal equilibrium with themselves, okay? So it just helps us define temperature, okay? This idea of when objects come into thermal equilibrium, okay? So, and that helps us understand like why, when we measure temperature, when we measure in Kelvin and we measure in Celsius, it's not, those numbers don't look the same, but it doesn't matter because we know that both of those scales are in thermal equilibrium with their environment. So that's the first thing that the Zeroth Law is trying to tell us. Do keep in mind that objects that have the same thermal energy, or objects may not have the same thermal energy when in equilibrium. So it's just something to keep in the back of your head, but we don't focus on that too much. Now the first law and second law are really about that thing I was talking about with the transfer of energy, okay? So the first law is the change in internal energy of a system is equal to the heat flow into that system, so how heat or energy flows in that system, plus the work done on that system. So another way to change temperature of a system, right, is if I have let's say I have a balloon has a large volume and it has a certain temperature, what I could do is I could decrease the volume of that balloon. If I decrease the volume of that balloon, what's going to happen is the pressure inside that balloon is going to increase because now it's a smaller volume. With that increase in pressure, the atoms inside that balloon are going to start to move faster, And if the atoms inside that balloon start to move faster, the temperature is going to increase. So I can transfer energy, right? I can come into a hot environment, and the hot environment will transfer energy into me, right? Same thing, you touch a hot stove, right? The hot stove's transferring energy into your fingers. So that's one way to get a change in temperature, right? We see the flow of heat from one system to the other. But another way is to do work on the system. Change the volume. You can expand a system and cool it down really quick. That's how refrigerators and things like that work. So that's what the first law is trying to tell us, okay? It's trying to just tell us that, right, the way the internal energy of a system, right, can be changed either by transferring heat, thermal energy to it, which is heat flow, or by doing work on it, changing the size of the system or something. The second law is again still trying to describe the same idea, where it's talking about disorder of the universe. So disorder of the universe never decreases. It's always increasing. We're always seeing an increase in disorder. And what that means is that when we talk about disorder, there's a lot of different ways to talk about it, but in this sense, we want to think about equilibrium. So the universe is trying to come into an equilibrium. Eventually, in a very, very long time, the universe, all the atoms in the universe are going to be equally spaced. So all the galaxies, all the stars, everything's going to fall apart eventually. I mean, we're talking about a long time, so I mean, the time that's going to take is very long, so I don't want to get into that. But that's what's happening. And it's dictated by the second law. So all the atoms are just trying to get equally spaced from each other. When they are, the entire universe will be in equilibrium at that point. Okay, and when all the atoms are equally spaced from each other, that we say the universe will be in disorder, total disorder. So that's what that idea means. There's no order. Order systems are when there's a lot of atoms clumped together, right? So like the human body is a very ordered system, where a lot of clumped atoms together. We fight this idea of disorder, this idea of entropy, right? That's why we're constantly needing to eat, because we're constantly needing to keep our bodies ordered. We've got to go against this law of thermodynamics. We've got to constantly be putting energy into us so that we don't go to disorder, and eventually we do, right? Eventually we pass away. So that's the idea. Sorry to get grim there for a second, but let's get happy again. Whee! All right, so second law of thermodynamics is just telling us that the disorder never increases or never decreases. It's always increasing, okay? And so with those systems, when systems start to go from high energy to low energy, which is really what this is trying to say, is that since order systems are very high energy and disordered systems are very low energy, all systems want to go from this very high energy to very low energy, which again, it's just describing that heat wants to go from a very high concentration to a low concentration. That's why when you come inside, you're very cold, your heat concentration is very low, and the air concentration heat is very high, and that high concentration of heat wants to go where there is no heat, so it goes to your body. That's what this law is trying to describe, okay? And those processes are irreversible. Don't worry about that too much, okay? But the idea is that energy or heat moves from high concentrations to low concentrations, okay? That's what the second law is trying to tell us, right? So these things are dictating why things come into thermal equilibrium, why a system will have the temperature it has, because the temperatures of systems can change based on what's going on. This is what's telling us that idea. And again, systems come into equilibrium, thermal equilibrium, by transferring energy, and you cannot transfer cold, so just keep in mind it's that heat transfer, right? Now down to this idea. So, how do we measure temperature? What are we measuring when we measure the temperature of a room? Well, the absolute temperature, which is what we call the temperature of the room, is determined when the measuring devices come into thermal equilibrium with the system or environment, okay? And our main unit in physics that we give temperature is Kelvin. Yes, there's Celsius, yes, there's Fahrenheit. Know how to convert those. I don't have this on here because that'll be for a different video. But temperatures in physics is measured in Kelvin. And just to give you some idea of Kelvin, when Kelvin's equal to 0, which is something we haven't actually seen yet, but we know it's a thing, that's when the molecules are not moving. We're going to talk about that in a second, but everything's just still. 0, okay? No velocity of the molecules in the system. Kelvin, when it's at 273, that's where water's freezing. That's where water's frozen. So we don't want to think that, like a lot of people might think, well, when water's frozen, isn't that when the molecules are moving? No, believe it or not, when water's frozen, the molecules are still jiggling. When Kelvin's 0, the atoms aren't even jiggling. They're just still. Okay? So don't think of just like velocity of the particles, but also think their oscillation, their jiggle. Okay? And so in freezing water, we got some jiggle, but not as much as like we would in boiling water. So Kelvin, when it's 373, that's boiling water. Okay, that's just, again, trying to give you some idea of when we talk about Kelvin and the scale of Kelvin, what it's actually telling us, okay? So, what are these measuring devices measuring? Well, we know a few things. These are these concepts you need to know. These are the things to understand. So this is the pressure kinetic energy theorem for temperature, where we know that the pressure of an ideal gas is proportional to the average kinetic energy of the molecules in the system, okay? And that's this equation. In this piece, pressure, there's the kinetic energy there, okay? N is the number of molecules, V is the volume here, okay? But the amount of pressure is proportional. It's directly proportional to the kinetic energy. So if pressure goes up in the system, kinetic energy goes up in the system. Now I want to make a point here. This is kind of important, okay? Now I'm going to tie something back to fluids here, but it's important. So in static fluids, we talked about a few ways to get changes in pressure. One was to apply a force to a fluid, and you apply a net force to a fluid, that net force will be felt throughout the fluid, right? Another way to get a change in pressure in a static fluid, remember, a static fluid, not flowing fluid, is due to depth, right? So the deeper you get in a static fluid, the more pressure increases. The third way that we didn't talk about in the fluids chapter, but what this is trying to tell you here is in a static fluid, not fluid flow, because you're going to get confused. In static fluids, the third way that we can increase pressure in a static fluid is by adding thermal energy to it. We add thermal energy to the system, we increase the kinetic energy of those particles, we're increasing the pressure. The reason why I'm pointing this out is because it's easy to get confused. We say in fluid flow that the faster the particles move, the less pressure they're implying to the environment. That's for fluid flow. This is not fluid flow. This is static fluids. So don't mix those. For fluid flow, that's 100% true. The faster the fluid moves, the less pressure it applies. The slower the fluid moves, the more pressure it applies to the environment. That's fluid flow. This is static fluids. So with static fluids, you can increase the pressure by increasing how fast the particles are moving in that container. Okay? Keep in mind, the particles are always moving in the container in a static fluid. Fluid flow is about the flow of fluid, not the moving of the particles in the container. Okay, so make sure you understand those things. And so if pressure is directly directed to kinetic energy, then we have this new relationship where the average kinetic energy that we've built, again, through physics and everything, you don't have to know how to derive these, but you do have to understand what they're telling you, that the average translational kinetic energy of the molecules in the system is proportional to the temperature, okay? So let's put all this together. The pressure of an ideal gas is directly proportional to the kinetic energy. So if the pressure goes up, the kinetic energy goes up. If the pressure goes down, the kinetic energy goes down. Okay, if the kinetic energy goes up in the system, then the temperature goes up in the system. If the kinetic energy goes down in the system, the temperature goes down in the system, okay? That's what this is trying to tell you. And in this equation, little k is Boltzmann's constant. It's not kinetic energy, that's a little k, right? It's lowercase k. Boltzmann's constant, it's this number, and T in this equation is temperature, all right? So what I just said is just right here. As pressure increases or decreases, translational kinetic energy increases or decreases, right? So as pressure increases, kinetic energy increases. As pressure decreases, kinetic energy decreases. Say it like that. As translational kinetic energy increases or decreases, temperature increases or decreases. So, as translational kinetic energy increases, temperature increases. As translational kinetic energy decreases, temperature decreases, okay? That's the concept. And then the last thing that we know is that as temperature increases or decreases in the system will expand or contract. Keep in mind, that's about work on the system. Okay? And so as temperature increases, the system will expand. As temperature decreases, the system will contract. That's the thing to understand. And the equation that explains that is right here, where L is the change in length of the system, L naught is the original length of the system, alpha is the coefficient of linear expansion, and temperature is the change in temperature of the system, okay? So we can look at the change in temperature and see how it's going to expand, see how the length of the system is going to change, okay? So that's the whole connection there, and that's what that's trying to tell you. So again, that's how we measure temperature. Temperature is what we talked about up here. How do we measure it? Well, we can measure the kinetic energy of the particles in the room, and the kinetic energy of the particles in the room are directly related to the pressure that those particles are doing, right? The amount of force that those particles are applying in the room, okay? And just don't forget what we talked about at the very beginning. Where this heat's coming from is that there's energy released in those collisions, okay? So the amount of thermal energy released with collision increases, right, with the speed of the molecules. So the faster the molecules are moving in the system, the more thermal energy is going to be released. The slower the particles are moving in the system, the less thermal energy is released. That's what we're saying there, okay? The next thing we do is we want to try to describe these systems and the changes in these systems, right? How they change based off the temperature or the volume, right? If we have a balloon at a certain volume and we heat it up, it's going to expand and get bigger. The volume can get bigger. How do we explain that, right? Well, for ideal gases, we have this ideal gas law that will allow us to describe those certain situations, right? So just keep in mind first what the ideal gas law is. And it's just telling us that constant volume, the pressure is proportional to temperature by the number of molecules or moles and Boltzmann's constant. Okay, so the pressure and volume are proportional to temperature is really what this is trying to say in the amount of moles in the system. Okay, and we can see that, right, P's pressure, V's volume, N here is number of moles, where N can also be thought of as little n, where N is the number of moles, 1, 2, 3, 4, and Na is Avogadro's number. Okay, and then when we write this equation out in terms of or when we write this concept out in terms of an actual equation, we see it's proportional by Boltzmann's constant here. So this equation right here, because we have two forms of it, this is the original equation. It's looking at what we call the microscopic version, where we can look at like individual atoms, different things like this. But when we have to look at cups of water, right, maybe gallons of liquids or gallons of gas, or this whole room, right, it's a huge container, right? Looking at the microscopic version, right, trying to count all the atoms in this room is just nuts, right? So what we do is we have the same equation, right, and I show you how they're the same, but we have the same equation that we consider the macroscopic version that can look at this, that can look at a room, right, that can look at the atoms in a room rather than like, so this is more for smaller containers, microscopic version. This one works for everything. Big rooms, small rooms, everything, all right? So this is typically the one we work with, where again, it's the same equation. These two are the same equation, where we can see this R, what we call the universal gas constant, is equal to this Kn. Okay, so when everything gets replaced, we end up with this equation right here. Again, they're the same equation. This is just the macroscopic version. This is the microscopic version. We like to use the macroscopic version. Just keep in mind, again, in here, N is number of moles, R is the universal gas constant, P's pressure, V's volume, T's temperature. Okay, so that's describing the pressure, volume, and temperature of a certain system at a certain time, right? But if it changes, we got to be able to look at how that system changes, and this equation allows us to do that, all right? So what we can do is we can take that equation and we can hold variables constant in order to look at different relationships in terms of how the system's changing, right? If I have a balloon that's in one pressure, volume, and temperature, then I change the pressure or temperature or volume, what's going to happen to the balloon? I can find those things out by setting this equation up for different relationships. So when moles are held constant, when we just hold moles constant, which we solve this whole equation just for NR, we can make, since this ideal gas law lets us look at both these, no matter how the system's changing, they'll both be equal to this equation. The initial part of the system and the final part of the system will both be equal to this. So because of that, we can make them equal to themselves. So once we establish this relationship, whatever we're trying to hold constant, we make this equation equal to. So here we're trying to hold pressure constant, volume constant, temperature constant. Here's moles. Okay? So when we hold the moles constant, we developed this relationship between the system where the initial pressure, volume, and temperature of the system is equal to the final pressure, volume, and temperature of the system. If you know all these three things, you can use this equation to solve for whatever you need in here. This just describes the relationship of how the system changes, the pressure and volume and temperature one time in the system, and then if we add heat to the balloon, what is the pressure and volume and temperature now? How does that look? This equation will describe that, okay? When we hold pressure and moles, so moles will always kind of be held constant. We're not going to be adding typically moles or adding atoms to our system. That will always stay constant. So moles will always be held constant, but we also end up holding like pressure or volume constant. So here, when moles and pressure are held constant, we first develop our relationship. When they're equal to themselves, the NR is going to cancel because the moles are also constant. So in this relationship, there's no NR because it canceled out. And so we're just left with T over V. So now we have the initial temperature and volume of the system is equal to the final temperature and volume of the system. So if you just have this in information, you can still talk about, you can't talk about the pressure of the system, but you know the temperature and the volume and the temperature of the other, you can find the volume. Okay, so this is just another way to establish a relationship with this equation. They typically in your book just show you this and assume you can do all these, okay? Because this equation will make all these. I'm just showing you what we actually do because a lot of students don't realize, hey, I can form these other relationships with the ideal gas law. Heck yeah, you can. So you should do it, and based off what you have, you can use what you need, okay? So when pressure and moles are held constant, this is the relationship we get set up. When volume and moles are held constant, this is the relationship that we set up, and if you know those things, you can use that relationship. And if temperature and moles are held constant, this is the relationship that's set up, and you can find anything. So based off what you know, based off what the question gives you, you can pick the ideal gas law that suits that question, suits the information in the question. Did they give me temperature and volume? And they want to know the other volume if I know the other temperature? Did they give me pressure and temperature? Did they give me pressure, temperature, and volume, and pressure and temperature of the other? Sometimes they give you all this information. This is the best one. We can do anything we need to, okay? And that's the idea. Okay, so the ideal gas law is based off this certain idea, and we can use it to describe the changes in the system. Because remember, in physics, we're always trying to look at the change in the system. The ideal gas law allows us to look at changes in the system, okay? Also keep in mind, and I should have described it, and that's my problem for putting it over here, but let's say we do, I hate to make a jump back, do need to solve for, let's say, the velocity of the particles in a system. Well, we can do that based off the two kinetic energies we know, right? We know there's a thermokinetic energy, and then we know that there's regular translational kinetic energy. What we can do is we can make these two things equal to themselves, which is what I did right here. Okay, and then the twos end up canceling, and we end up with this equation here. So I will make the argument that this is probably the most important equation out of everything down here, because with this equation you can find velocity, temperature, right, what you need, but what we typically do in this class is use this equation to solve for velocity. So that's what I did here. But keep in mind, you don't have to solve this. You can solve this equation for temperature, okay, if you know how fast the molecules are moving, right? Just make sure you understand what all these variables are in the equation, right? V's velocity, T's temperature, K's Boltzmann's constant, and M in there is the mass of the atoms, okay? So even when you get this velocity equation, right, 3 is 3, K's Boltzmann constant, T's temperature, M is the mass of the atoms. So we need to talk about what the heck that means, the mass of the atoms, all right? But keep in mind, I didn't mean to make a jump because we were talking about ideal gas law, but just keep in mind that you can, based off of this pressure kinetic energy theorem, we can solve for the velocity of the particles in a system. So if I needed to know how fast the atoms were moving in this room, I could figure it out if I knew the temperature. Like, oh, it's 80 degrees in that room, right? In terms of Celsius, I'd have to transfer that over to Kelvin, because that's what that number would be. So I transfer my Celsius number over to Kelvin, and if I knew, right, what this room is mainly nitrogen, but there's some oxygen, but since it's mainly nitrogen, we would say, okay, well, what's just the velocity of the nitrogen in the room, right? We can find that out. We find the mass of the nitrogen in the room, then we can find out the velocity of the oxygen in the room. The same thing, the velocity of the carbon in the room. This, okay? That mass number will change, right? For the nitrogen, that'd be the mass of the nitrogen in the room. For the oxygen, that'd be the mass of the oxygen. So what the heck does that mean? Well, like I said, when we're talking about temperature here, we're talking about all the particles tapping on you, hitting you, right? It's not like when air hits you, but air is actually just a bunch of molecules, right? Those molecules are hitting you. It's the atoms that we're talking about. So when we're talking about systems, we talk about them in terms of atoms. So let's just make sure we understand what we're talking about when we're talking about atoms, all right? And this idea of moles and why we use moles and why we're even using this idea of the macroscopic version. So first of all, we want to know how to look at atoms in a system, okay? So if we're just talking about one atom, okay, then the mass of that atom, what we call the atomic mass of the atoms, are given by the periodic table. It's the numbers. You see like nitrogen's going to be a big N. The number right underneath it, those are all what we call the atomic mass. So like for carbon, for example, sorry, there's a periodic table right here I'm pointing at, so I know it's probably weird. But for carbon, for example, we know it's 12.01, and the units for those numbers for the atomic mass on the periodic table is grams per mole. Okay, so we know that's what we call the atomic mass for carbon. If someone asks you what's the molecular weight for carbon, well, it's 12 times that U, which U is equal to this, but the thing is that when you multiply that U is 10 to the negative 27. It's a very, very tiny number. So when you multiply U by this 12, you're essentially getting this number again. Okay, just keep in mind this is kilograms over here. This is grams per mole, okay? So they're roughly the same, but not necessarily. We'll talk about that down here, all right? So just keep that in mind, all right? Again, one atom is equal to the atomic mass, the numbers given on the periodic table. One example, like for carbon, is 12.01. For oxygen, it's 16.00. Okay, so those numbers are on there. 16.00 grams per mole for oxygen. Okay, you can find all these things are givens, right? So if you have 2 carbon atoms, for example, right, then you just multiply 2 by that number. So if you want the atomic mass of those 2 carbons, it's 2 times 12.01 grams per mole. Or if you need the molecular weight of those 2 carbon atoms, you can do 2 times 12 times that U. Okay? So either way, I just want to make sure you understand this idea. So each atom has essentially a mass to it. That mass is given by the periodic table. If we're trying to look at a system that just has one atom in it, then this is going to be the mass of the atom, right? If we're looking at a system that has only 2 carbon atoms or 3 carbon atoms in it, then we want to take this number and multiply it by 3, okay, to know how much, right? We'll know how much in terms of the mass, what's the total mass of the total carbon in the room, okay? Now, if we're not talking about individual molecules like 1 carbon or 2 carbon or even 15 carbons, 12 carbons, things like that, we start to talk about them in moles. So first of all, understand a mole is just a way to describe a group of atoms, okay? So you know how we call 12, a group of 12 of something a dozen. So 12 eggs equals a dozen eggs, right? A dozen equals 12 of something. That's the same way to think of a mole. So if someone tells you you have a dozen eggs, you know that you have 12 eggs, right? Well, someone tells you you have a mole of carbon, you know that you have this many atoms of carbon. If someone tells you you have a mole of oxygen, the number doesn't change. You have this 6.022 times 10 to the 23 atoms, which is a huge freaking number, right? That's how many is in oxygen. So think of a mole just as you were a dozen, right? If you have 4 dozen, right, you take 12 times 4, right? Same thing here, okay? 4 moles of carbon is this times 4. That's how many atoms that's equal to. It's that simple, okay? That's how this idea of a mole works. So when we're looking at big rooms like this, we want to look at the amount of moles in the room rather than look at the individual particles. And so that's the nice thing about this mole. But we got to be careful because when we're using moles, we got to understand just how to convert back and forth between the small and large. Okay? So for this first this is all just conversions now for the rest of this video. So know that this is just showing you how to convert the different things to use over here, all right? So the first example is grams of moles. To go from grams of, if they tell you have 18 grams of oxygen, how to go from that number to how many moles? I might say, how many moles do you have? If you have 18 grams of oxygen, how many moles of oxygen do you have? Well, this is how you do it. You take that 18 grams, you multiply it by its molecular mass, and what we're doing here is dimensional analysis. So we're trying to cancel out units to be left with the unit that we want, right? So if we're looking for moles, we need to be left with the unit moles, and this will give it. These grams will cancel, we'll be left with moles. Whatever number we get, it's going to be that amount of moles, right? So it's the mass of the atoms, whatever it may be, 18 grams, 15 grams, whatever they'll tell you. You have 25 grams of copper. That's what number would go here. And then if it's copper, then the atomic mass of copper would go there. If it's oxygen, then the atomic mass of oxygen, which is what we used here, would go there, okay? When you multiply those two things together, the way that we did, right, the number of moles. Now, why did I say the way that we did? Because we know, right, that this is written in grams per mole, right? So for oxygen, right, its atomic mass is 16.00 grams per mole, okay? But look how we have it written here. We have it 1 mole per 16 grams. Well, we can write this conversion factor. We can write this any way we want to. We can write with the 16 grams on top and the mole on the bottom, or we can write this with 1 mole on top and 16 grams on the bottom. It doesn't matter because it's still the same ratio, okay? What we're trying to do is we're trying to cancel out the units. So you need to figure out, right? We say multiply the atomic mass. You need to figure out, you've got to write the atomic mass like this or like this based off what you're trying to cancel out. I'm trying to cancel out grams. So I want this version. I want the grams on the bottom so they cancel, and I want moles to be left, and that's what's left on top here, right? Let's say I wanted moles to cancel and I wanted to be left with grams. Well, then I'd want to use this one, okay? We'll see that here in a second. Okay, so this is how to go from gram, right? So if I take the atomic mass, take the mass of the atoms, multiply it by the atomic mass, and make sure that I write that conversion properly, I'm going to get the number of moles that are there, okay? Now, if I want to go from grams to number of atoms, right? Here again, we're just using oxygen as an example. Let's say I have 18, they tell you have 18 grams of oxygen. How many atoms do you have? Well, it's just an extension of what we just did before. You take those 18 grams, right? We need those grams to cancel. Why? Because we know that the atoms conversion, that Avogadro's number, right? Which I probably should have paid more attention to, but this thing right here, this is Avogadro's number, is 6.022 times 10 to the 23 atoms per mole, right? Well, I know that if I can get these moles to cancel in this conversion, I'll be left with atoms, and that's what I'm looking for. How many atoms are here? And that's what we do. So here I write the conversion factor again. I pick the one with the mole on top, 16 grams on the bottom. And again, this is the atomic mass, the mass that I found off the periodic table. I cancel out the grams, I'm left with moles, right? And then I take Avogadro's number, which is atoms per mole. And again, this can be written either way. This can be written 6.022 times 10 to the 23, right? Atoms per mole, right? Or it can be written 1 mole for 6.22 times 10 to the 23 atoms, right? Either way, right? You have to just decide, do I need this version of it or this version of it? How do you decide? You decide by what needs to cancel. Here we want grams to cancel, here we want moles to cancel. So I want this version. I want the moles to cancel, so these moles will cancel, and I'm left with just atoms, and that will be the number of atoms. So what are we doing? We're taking the mass that was given, however many grams. We're multiplying that by the atomic mass. And keep in mind, if they give you kilograms, you got to convert to grams because this is grams, not kilograms. We took the atomic mass from the periodic table of whatever the thing they were asking for. Here it was oxygen. Could be carbon, then it would be atomic mass of carbon. And we multiplied it by Avogadro's number to get the number of atoms. Okay, so that's how to convert that. Mass is small number of atoms. okay? So how do we get the mass of atoms? Let's say for oxygen, there's another way to get the mass of atoms. So one way is what we're doing up here. Another way, a quick way. And when you're saying, what do you mean, how do we just jump to this mass of atoms? Well, it was this down here, right? This is mass of atoms. How do you get this mass of atoms? Like I said, what if we wanted just the mass of the atoms of the nitrogen in the room? Well, this would be how you get it, okay? Let's say that there's 3 nitrogen atoms in the room. I'm just throwing some out there. So you write 3 here. There's a number of atoms, right? And then you take the atomic mass, again, whatever it is, whatever's going on up there, right? If it's of oxygen, you put it in there, right? If it's of nitrogen, you put it in there. Nitrogen's 14.01. So if this was nitrogen, it'd be 2 times 14. Here again, I'm doing oxygen. So I want to know, like, the mass of 2 oxygen atoms. So it would just be 2 times the atomic mass times that mu, okay? That will give me the mass of the atoms, okay, or the molecular weight of the atoms, which is what needs to go in there. Okay, so if you need the mass, okay, of the atoms, this is how you do it. So just keep in mind, I have all these conversions labeled. Each one of these conversions is showing you something different, all right? And for the last conversion, how many atoms in a certain amount of moles? Well, if they tell you, like, you have 12 moles, how many number of atoms do you have? Let's say they say, oh, you have 12 moles of oxygen. What you need to do is you got those 12 moles of oxygen, right? You have Avogadro's number. You multiply by that 6.22 because moles are moles, right? Just like I said up here, okay? If I have 12 moles, I have 12 moles, okay? And those moles are going to be this many atoms. So if I know how many moles I have, I can just multiply by that Avogadro's number, and I know how many atoms I have. Because it doesn't matter if it's oxygen or carbon or phosphorus, all of those, the moles are 6.002 times 10 to the 23rd atoms. Okay, so you don't have to be specific down here. No matter if it's 12 moles of oxygen or 12 moles of nitrogen, this is how many atoms are going to be there, because the amount of moles of oxygen and the amount of moles of carbon are going to be the same. Now, let's say you have 18 grams of oxygen. Well, what you need to do is you need to first get the amount of 18 grams, right? Or you need to get the amount of moles of 18 grams, which is what we do here, and that's what this conversion factor is doing, and then multiplying by the atoms to get the number of atoms, right? So I probably should have shown this one first and shown this one last, because this is actually a shorter version of this, but just keep in mind what we're saying up here, okay? So this is grams to moles, this is grams to number of atoms, this is just finding the mass of atoms, of small amounts of atoms, and this is how many atoms in a certain amount of moles, okay? Hopefully that wasn't confusing. This one's just really straightforward. Just the idea of moles can be confusing, so I just wanted to reintroduce it again, all right? Thank you so much for watching. I hope this was helpful. Again, keep in mind what temperature is, okay? And keep in mind what happens when things come into thermal equilibrium. There's transfers of energy. Heat goes from high concentrations to low concentrations. So if you're feeling warm, if you're warming up, you must be gaining heat. If you're feeling cold, or the system is getting cold, it must be losing heat, okay? Cold can't transfer. Cold just comes by the slowing down of the molecules. The slower the molecules are flowing, the colder that environment's going to feel, the colder that system's going to feel. The faster those particles are moving in the system, the warmer it's going to feel. You take that system and you put it in another system that isn't at the same temperature, those systems will always come into equilibrium by transferring the system that has the higher energy to the system that has the lower thermal energy, okay? Because energy moves from high concentrations to low concentrations. All right, well, I hope this was helpful. Keep all that in mind. That was a lot to talk about. I'm super proud of you, and I'll see you on the next video.